Hello guys, Mrs. Levenseller here, and we're going to go back and talk a little bit more about rational and irrational numbers, okay? So your learning targets for this video are 1B, I understand the differences between a rational and irrational number, and 1D, I can compare values of rational and irrational numbers, including negatives and absolute value quantities, okay? So let's talk about rational and irrational numbers. We briefly looked at them in the last video. Rational numbers, if you think about the word rational, like somebody who's a rational thinker, they have very organized, very neat and tidy thoughts, right? And irrational people or irrational thinkers, they might be a little bit scattered, a little bit impulsive, a little bit crazy, we might even say. So I want you to think about that with numbers as well, okay? So rational numbers are numbers that you can make into nice, tidy little fractions, or ratios, as the beginning of that word says. So anything you can write as a fraction or as a ratio is a rational number. That means we could have integers like we looked at before, so like -3. Well, we could write that as -3/1. It's the ratio of -3 to 1. We could have whole numbers, maybe like 5, right? Or 0. 0 can be written as 0/1 or 0 over anything. 5 could be written as 5/1. Natural numbers are part of the rational numbers. Again, 5 is another example of a natural number. And you can also have just decimals or any other kind of fractions. So 2/3, that's rational because we can write it as a ratio or a fraction, 2 to 3. And let's say we had the fraction, the decimal, 0.5, right? Well, that is, if we convert it into a fraction or a ratio, 5/10 or 1/2, right? So decimals that terminate or decimals that repeat, those can all be written as fractions, so those are all rational numbers. So a repeating decimal works too, like 0.111, etc. Repeat, that is the same thing as 1/9, okay? So anything like that we can write as a fraction. Now on the other side of this here are irrational numbers. Those are numbers that get a little crazy. So things that don't, decimals that don't terminate or don't repeat. Probably one of the more famous ones is pi, right? 3.1415926, ... Those are not in a pattern. Those decimal values are not in a pattern like 0.1 repeating, right? Those are different kinds of things. So that would be an example of an irrational number. Another really famous one is the square root of 2. If you get into higher math, we use that a lot as an example of an irrational number. If you want to know what the decimal version of that is, go to your calculator and do 2 and then the square root button. Look at that decimal, 1.4142135, blah, 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 right? That is not a rational number, okay? So anything that doesn't repeat or doesn't terminate, it doesn't stop, has to be irrational, okay? So let's compare some of those numbers and see what we think, whether they're rational or irrational. And we want to use certainly our mental math strategies to approximate the radicals, but if you can't quite determine if it's going to be rational or irrational, you can go to your calculator and find the square root and double check, okay? So let's compare 6 and the square root of 31. Now when we're comparing different values, what do you think is a good strategy, right? Pause the video and think about that for a second. What's a good strategy for us to compare two different values? So hopefully you've had a second to think about that. So comparing two different values, I think one really good strategy is to make them look similar or make them in the same form. So what I mean by that is if I have 6, which is a whole number, and I have the square root of 31, I either want to write both of these as a square root or I want to write both of them as just regular real numbers, okay? So 6, I can rewrite that as a radical. We talked about this last time. That's equivalent to the square root of 36, right? And over here we have the square root of 31. So if we're comparing them, compare means which one's greater, which one's smaller, or are they equal to each other? Well, the square root of 36 must be bigger than the square root of 31. So 6 is greater than the square root of 31, right? Think about whether they're rational or irrational. Well, 6 is a whole number, so that's got to be rational. Excuse me, I just sneezed. And the square root of 31 is not a perfect square, right? So we can assume that that is irrational. Again, you could check on your calculator. 31 square root. Yeah, that's not a rational number, okay? We know it had to be less than 6, but it is not rational, so that's irrational there. Okay. Now what about 0.4 and 2/5? Let's put them in the same form. So either you can convert 0.4 into a fraction or 2/5 into a decimal. Well, going from a decimal to a fraction is easier for me, so I'm going to rewrite that as 4/10, right? We would read this decimal as 4/10. That's literally what it turns into as a fraction, okay? So let's compare 4/10 and 2/5. Well, 4/10, if I reduce that, reduces to 2/5. 2/5 is already 2/5, so these two are actually equal, all right? When you want to decide if either is rational or irrational, ask yourself, can they be written as fractions? Well, 4/10 was definitely able to be written as a fraction. Sorry, that's too dark. And 2/5 is already written as a fraction, so these are both rational. All right, let's try a couple more. So here I'm throwing an absolute value at you. Remember, we talked about the absolute value being a number's distance from 0. So if I'm looking at the number -7, I want to know what's the absolute value of -7. Well, it has to be 7 spaces away from 0. So I'm turning this into a real number here. And the square root of 225, do we know what that is? Hopefully. Square root of 225 would be 15. That's a perfect square. So comparing 7 and 15, I just had to turn those into the same form. They're both into real numbers now. 7 is less than 15. That was a really poor symbol. Less than 15. So we can write it as 7 less than 15, like a math sentence here. All right, the last two. These two are symbols, right? Symbols we might use in math. So the first one is pi, and hopefully you know what pi is equivalent to by now, but pi, if I turn these into decimal values, it's hard to compare two symbols, 3.14159 ... Okay. Now, E is a number you might not have heard of yet. When you get into Algebra 2 and into your physics class or chemistry class, you'll talk about natural logs. Maybe when you talk about carbon dating, you might have heard of that already. Radioactive decay, things like that. E is a number that comes up a lot in those type of situations. So just like pi, E represents a value. And on your calculator, you should have an E button just like you have a pi button. So E, it's showing us is 2.71828. 2.71828. All right, so now that we've written those in the same form, first of all, both of these would be irrational numbers, right? Those are non-terminating, non-repeating decimals. So both irrational. And which one is larger? Well, pi is larger than E, all right? And I think we forgot to mention up here, but 7 is less than 15. 7 and 15 are both rational numbers. Oh, geez. All right. And that about